Thank you. So hello everyone. We're okay, right? Hello everyone. My name is Sayit-Bolluk and I'm from Özyeğin University. I'm a PhD student at Özyeğin University. Today I will present my study called a Simplified Bayesian approach for the calibration of district building energy models. So, dynamic building energy models are common tools in assessing the urban building energy performance. And these models are great tools to accurately predict the building energy consumption at the high temporal and spatial resolution. However, simulating them might be costly in terms of time and computational resources. Optimizing these dynamic models are exhaustive since there is no direct mathematical solution that clarifies the simulation process. So to deal with these black box nature of the simulation process, surrogate models are highly utilized in the sense of Bayesian optimization. These models the surrogate models are very common tools to imitate and replace the dynamic simulation while reducing the computational time. However, they might ignore the complex interaction raised from the high uncertainty in the urban building stocks. So therefore, to provide the solution for this, we propose an optimization approach that reduces the computational time while avoiding the reliance on a surrogate model. So this is our methodology. We start with building a dynamic model, and we created different parameter combinations from the simulation parameters and simulate them to obtain monthly simulation results. Then we labeled these scenarios based on a predetermined error limit and build a classifier over these labeled scenarios, and finally obtained the ideal values for each simulation parameters and created the Bayesian model. So let's start with the first phase. So we utilized the urban modeling interface by MIT Sustainable Design Lab to create our dynamic model. This model is integrated into a CAD software called Rhinoceros 3D. And it has three main inputs, which are the building template, building geometries, and the weather data. So building templates involve many simulation parameters, such as building envelope properties, HVAC details, and the building operational schedules. We created different optimization scenarios from the combinations of these simulation parameters and simulated them to obtain the monthly energy consumption data. So we compared these simulation results with the method consumption data and measured the simulation error based on an error metric called the coefficient of variation of the root mean square error. As relevance standard, which is ASHRAE guideline, suggests that the simulation or the prediction error of a building energy model should not exceed the 15% of CVRM-SE at the monthly resolution. Based on this, we labeled the scenarios with having less than 15% of CVRM-SE with label 1 and 0 otherwise. The label 1 scenarios are considered as desired, and the other scenarios are considered as the undesired scenarios. We also utilize another classification metric, evaluation metric called mean absolute percentage error to validate our simulation results. So once we label each scenario, the optimization becomes a binary classification task where the features are the simulation combinations of the simulation parameters and the targets are the labels. So here we try to understand what makes a scenario desirable or undesirable and to what extent. So our aim is to drive posterior probability distributions for the 0 and 1s, which are the desired and undesired scenario labels, using the Bayes formula in equation 3. So we have two assumptions here. The first one is that we assume that each simulation parameter given a scenario label is assumed to be independent from each other. This makes our assumption a naive classifier. So based on this, the likelihood becomes a multivariate likelihood, and the second assumption is that we assume that the likelihoods are having a Gaussian distribution. So we model them as Gaussian probability distribution functions. After training the Bayes classifier over the labeled scenarios, our aim is now to find the optimal value of each simulation parameters. To do that, we utilize the posterior distribution of the label 1 scenarios in other terms, the desired scenarios. So we assume that the expected value of each posterior distribution gives you the optimal value for that scenario label. Since the desired scenarios are the ones we want to have, we utilize the posterior distributions of the label 1 scenarios given the simulation parameter, for example, the infiltration ratio. And we updated the human template with these optimized simulation parameter combinations and run a final simulation to obtain the monthly energy results for the optimized model. So we tested our methodology over a dormitory district of Özyeğin University in Istanbul. There are 6 buildings at this campus, and our target end use is the summation of the natural gas and electricity consumption at the monthly resolution. We utilize different data sources, for example, energy audit reports for driving the building templates, characterizing the building templates, the Yandex map constructor and UBAM.io platform to drive the building geometries from building footprints, and also merge the building templates with the building geometries to create the final dynamic model. And finally, the Turkish State Meteorological Service to obtain the weather data. We performed the simulation between September 2018 to 2023 because this is the term that we have available for the weather data. So we needed to select the determinant simulation parameters because our aim is also to reduce the computational time. So to do this, we checked the building energy audit reports available on the campus, and we saw that some parameters does not have prior knowledge in those reports. For example, the infiltration ratio, equipment power density, lighting power density, and the domestic hot water flow rate does not have any knowledge on the energy audit reports. Therefore, we assume that these parameters desire consideration in the optimization. Also, since the campus energy demand is driven by the heating, we selected the heating set point using our engineering judgment. Overall, we chose 5 simulation parameters and evaluated 5 different values of these parameters, makes 3,125 scenarios to be evaluated during optimization. After creating these scenarios, we simulated them, we measured the scenario error, and we applied the Bayesian approach. Overall, we have 3 different models. The first one is the baseline model, which consists of the baseline combination, and the baseline combination is the average initial values of these simulation parameters. The second model is a deterministic model, which is created by the deterministic combination obtained from the scenario with the least simulation error, and the final model is the Bayesian model, characterized with the Bayesian combination, and this is the combination where we applied our approach and come up with. So we characterize each model with its relevant combination and perform a final dynamic energy simulation. And here are the results based on the total operational energy consumption at the monthly resolution. We see that the deterministic model outperformed the other models with the least monthly simulation error of 8% CV RMSE. Also, we see that the optimization with both deterministic and Bayesian model increased the baseline error drastically. However, we see there might be some, let's say that the results for the deterministic model might be deceptive. Let's check the natural gas and electricity errors based on the natural gas and electricity use items. We see that Bayesian model for both MAPE and CVRSME, the Bayesian model achieved a more balanced distribution between the natural gas and electricity errors. As you can see, the average error for the Bayesian model is 26.7%, and while the deterministic model provided 31.8% error. So, by selecting the scenario with the least simulation error, the deterministic model might ignore the complex interaction between the simulation parameters and the method consumption data. Thus, it cannot match the consumption data better. On the other hand, the probabilistic optimization with the simplified Bayesian approach provided more stable and accurate electricity and natural gas consumption simulations with the use of a new defined set of simulation parameters rather than relying on the predetermined scenarios. So there are some possible future directions that we can improve the results of our approach. First one is the naive assumption of the classifier. We assume that our likelihoods are independent of each other. However, this might not be the case in the reality. So modeling these likelihoods as a multivariate dependent probabilities might improve the optimization results, as it can consider the complex interaction between the simulation parameters and the resultant energy consumption. And the next one is the assumption of a Gaussian distribution. We assume that each simulation parameters has a normal distribution, but none of the simulation parameters does not have to have a certain probability distribution. So utilizing non-parametric classifiers such as decision tree can help us to extract the non-relay relation in the data and improve the classification performance. And finally, just a second, we have a highly imbalanced target distribution. For example, 90% of the scenarios as labeled as desired, where only 10% of the scenarios as labeled as desired scenarios. And this caused an imbalanced target distribution, and it affects the model decision process, while it tends to label scenarios as undesired because there are lots of undesired observation. So if we can handle this imbalanced target distribution, we can enhance the performance of the classification. So let's conclude. We see that the Bayesian model decreased the baseline model simulation error with 45%, and we saw that the Bayesian model provided more balanced and precise simulation results compared to the deterministic approach based on natural gas and electricity items. So this model is effective and accurate for district or urban level studies, and it can be utilized for the urban building energy performance assessment with the dynamic simulation, where the actual objective function is not easily accessible. Thank you for your time.